Next topic, group 17th. Okay, this is a halogen group. So here we have to remember boiling point order. So as I explained in 15th group, that lesson, the boiling point order will be sorry, for if we will take HI, HBr, HCl and HF, the boiling point order will be HF is more than HI, then HCl, at last HBr. So this I have explained in a 15th group, that lecture. It is there in my channel. You just see why it's coming like this. And also when we have a F2, Cl2, Br2 and Hi2, so here also we have to see the boiling point order. So boiling point is directly proportional to the bond length, we can say like this. Okay, if higher the bond length, then higher will be the boiling point. So since hydrogen size is bigger, the bond length is more. So because of that, I2 is having more bond length than Br2, then Cl2, at last F2. And then another important thing in this uh, chapter is I2. So I2 shows two kinds of colors. So I2 shows purple color and also red brown color. So it shows purple color in the nonpolar solvents. When we dissolve I2 in a nonpolar solvent, it shows a purple color. Nonpolar solvent like Xane, these things, it shows a purple color. So when we dissolve this one in the polar solvents, so it shows a red brown color. So this is because of the formation of I3 minus. So I3 minus is forming in the both polar solvents as well as non-polar solvents. So because of that, the color is changing. Okay, so this is important. It's better to remember this. And then yeah, then the important thing is like IF7. The shape of IF7 is also important. So it exists in a pentagonal bipyramidal. This is exist in a 4, 5, 6, 7. So it exists in pentagonal bipyramidal, and this comes under D5H point group. Okay, then we have I3 plus, I5 plus, and these two also important. So I3 plus shows we know how to calculate hybridization, like this is 7th group element and one positive charge is there, means it will be 6, 3, 4, 5, 6. Since iodine is a monovalent and here 2 are there, so total 4 bonding orbitals there. So this is a sp3 hybridization. So sp3 hybridization with 2 lone pairs, it shows a V shape. So this is the IF5 plus structure. Here 3 iodines are on the plane, means like linear. So one iodine is on the top, another iodine is down. So this is the structure of IF5, and we'll go for the MOT of halogens. MOT of I2, Cl2, Br2 and F2. Okay, so F2 shows one type of MOT and remaining Cl2, Br2 and I2 shows same kind of MOT. So only fluorine shows different MOT and remaining 3 compound shows same MOT. So we know that F2 is having NS2 NP 5, total 7 electrons, 7 plus 7, 14 electrons are there. So this is the MOT for fluorine. So here we have, this is sigma 1G and this sigma 1U. And then this is sigma 2z, and this is 1 pi u, and this is 1 pi g, and this is 2 sigma u. Okay, so we have 14 electrons, 1 2 3 4 5 6 7 8 9 10 11 12 13 14 electrons are there. So for Cl to Br to I2, the MOT will be like this. So this will be same, and this will change for these three compounds. Here we have, this is 1 pi u, this is sigma 2g, this is 1 pi g, this is 2 sigma u, and here we have 10 electrons. It will feel like this. Okay, and this I did not write here, this orbital. And now what we need to remember here, so for F2 to sigma 2g orbital is coming down, but here it's coming up. So in case of fluorine, what you need to remember is that this is because of this is having a pyz orbital. Okay, and 1 pi u is having a pxy and pzx orbitals, but here 1 pi u is having a pyz orbital, and this is having pxy and pzx. Okay, so the only thing, the only difference is here for MOT of fluorine and remaining halogens, that this orbital is different. So for fluorine, this is 2 sigma z, and it is due to, like, this is having a pyz orbital, whereas for 1 pi u we have a pxy and pyz, and here this term only gets reversed, and this will be same. Antibonding orbital will be same in the both the cases, only bonding orbitals are showing differences. And they may ask, like, which one is a single degenerate, which one is a double degenerate. So this is single degenerate here, because only one orbital is there, and this is a double degenerate. So for in case of fluorine, sigma 2g is a single degenerate, whereas in case of chlorine, bromine and iodine, so this is the double degenerate. And so this is the point you need to remember. And here in case of fluorine, 1 pi u is a double degenerate. In case of other halogens, it is a single degenerate. Okay, and then there may be possible that if it is in excited state, and this electron may go here. Okay, this is fine. So just you need to remember this one. Here we can they may ask what is the second homo orbital. So in case of chlorine, bromine, iodine, second homo orbital is 2g, and here second homo orbital is 1 pi u. So these are important points you have to remember about MOT diagram. The next point is dissociation energy. Dissociation, bond dissociation enthalpy. So what is a bond dissociation enthalpy? So there is a bond. The energy required to break this bond is called as the bond dissociation energy. If smaller the bond length is smaller, we need more energy, and if bond length is bigger, we need less energy. Okay, now so if we see the bond length, bond energy, bond length order, so you know that iodine is a bigger in size, so that's why the bond length will be more, right? So bond length order will be I2, then Br2, then Cl2, and then F2. So this is a bond length order. So bond dissociation energy, bond dissociation enthalpy will be in the reverse way, that F2 Cl2, Br2 and I2, because so this is having more bond length, so more the bond length means we require a less bond dissociation enthalpy. But and this is the expected order of bond dissociation enthalpy. But the reality, in the reality, the order will be chlorine, then bromine, then fluorine, then I2. So this is the correct order for bond dissociation enthalpy. Bond dissociation enthalpy. So why chlorine is coming first? So there is a we know that electron affinity. So because of electron affinity, chlorine is having a more dissociation enthalpy, and then fluorine, so coming to F2, what is happening? So since this is a small size, so there is a repulsions are there. Because of that, the bond length will increases. So when bond length is increasing, automatically what is happening, this bond is becoming weaker. So that's why fluorine is coming here, and anyway iodine is least because bigger in size. So this is the correct order. So Cl2 is having a more bond dissociation enthalpy because of the more electron affinity. Is oxidizing power of halogens. So this order will be F2, Cl2, Br2, I2. So oxidizing power of F2 is highest because we know that F is having a small in size. So because of small size, there is a repulsions between the two fluorine atoms, and because of that, this bond is very weak and we require very less activation energy to break this bond. Okay, what is the oxidizing power? Oxidizing power means that atom itself undergoes oxidation and it reduces the another one. That means if F is there and it gives one electrons, and it will make another species as a X minus. So here F is getting oxidized and it's reducing another species. So this is called as a oxidizing power. Okay, so F2 is a stronger oxidizing power, then Cl2, then Br2, and then I2. If they ask reducing power, then it will be in the reverse. So I2 is having more reducing power, then Br2, then Cl2, and then F2. So next we have Lewis acids and base concept. So in this chapter, so this is very important because here we have SBF5. This is upon treatment with SHF, we get a SBF6 minus plus H plus. So if we will take this as 2 molecule, then this will be H2F plus, like that. So they may ask which one is the base and which one is the acid. So which one is fluoride donor is base and fluoride acceptor is acid. So this topic is very important. I am not going into details in this topic because there is a one video 9 aqueous solution. I have uploaded that video long back, so you just refer that video. I have explained each and everything in the detail, so that's why I'm not going here in the details. And here we have two important topics: cationic interhalogens and anionic interhalogens. The examples for cationic interhalogens are I2 plus, I3 plus, and I5 plus. And for this we have I3 minus and I5 minus, and this one Br2 plus also comes here. Okay, and this we can prepare when we have I2. If we treat this one with H2SO4, so here we get I2 plus. And here structures are very important. So I3 plus structure I have explained already. This is a C2 point group that looks like a V shape. Okay, then I5 also I explained, it looks like this. 3 iodines are arranged linearly. One iodine is on the top, another iodine is in the bottom, and these bond lengths will be different. Okay, they will not be having same bond lengths. So this is some 90 and this is some 200, like that, and this also different. So this is about the cationic interhalogens. And next important is anionic interhalogens. So this we call it as a polyhalides. So when I started this lecture, I said that I2, when we dissolve it in a polar solvents, so and I2 in a non-polar solvents, so they are showing a different colors. So because of the formation of I3 minus. So I3 minus is what? Anionic interhalogens. So we also call it as a polyhalides. Due to formation of polyhalides, the iodine color is different from the polar solvents to non-polar solvents. And similarly, when we take iodine and it is dissolved, when we dissolve this one in I minus solution, so here we'll get I3 minus and I5 minus. So here also, upon dissolving I2 in a I minus solution, here also the new color will develop. New color will develops. Okay. Then we go for I3 minus structure. So this is having a trigonal bipyramidal structure with 3 lone pairs. So these 3 lone pairs will occupy 3 equatorial positions, here, here, and here, here, like this. Okay, and the MOT will be like this. So this is bonding orbitals, and this is non-bonding orbitals, and this is anti-bonding orbitals. So total how many bonding electrons here? 4 bonding electrons. So those 4 bonding electrons we can arrange like this. And the possible question may be, what is the home orbital in a I3 minus? The home orbital is this non-bonding orbitals, and LUMO orbital will be anti-bonding orbitals. So this may be possible question. Okay, and then they will go for I3 minus structure. Sorry, yeah. So sorry, this is I3, right? So then the bond length from this bond length and this bond length, it will show some differences. So this bond length will be around 310 pm, and this bond length is around 282 pm. So because of this lone pair interactions, some distortions will happen in this I3 minus structure. So due to these distortions, the bond lengths will be different. You don't need to remember these values, but they may ask why the bond lengths of 2 iodines in I3 minus is different. So this is due to the distortion of the lone pairs. We can say that just distortion is sufficient. And what is the importance of this polyhalides? So polyhalides can conduct the electricity, means it can show the electrical conductivity. Okay, due to like see what is the thing we require to conduct the electrical conductivity? We just require some lone pairs or some electrons. So we have these electrons. So these electrons also can conduct the electrical conductivity. And then shapes also varies. In this chapter, mostly the question will comes from the shape only. So I of 6 minus, what is the shape of I of 6 minus? So first we will calculate the hybridization for it. So this is the 7th group element, and this will be 8th, 2, 3, 4, 5, 6, 7, 8, and 1 fluorine, 6 fluorines are bonding, 3, 4, 5, 6, and 1 lone pair is there. So this is having a sp3d 3 hybridization, because 1, 2, 3, 4, 5, 6, 7 bonding orbitals, and 3, 3, 6, 1, 2, 3, 4, 5, 6, yeah, sp3d3. So there is a difference between the geometry and shape. Okay, and the shape of this compound is distorted octahedral. And if they ask geometry, this will be pentagonal bipyramidal. Okay, and means don't get confused. When we will take water, the shape of water is V shape, but when they ask geometry, what is the geometry of water? That is the tetrahedral. Okay, because this is sp3 hybridization, so sp3 hybridization geometry has to be tetrahedral. So that is the difference between geometry and shape. When they ask shape, this is V shape, and they ask geometry, it will comes under the tetrahedral.